back to our fourth video in our series on integral calculus. This video is going to be discussing the antiderivative rules for polynomials. We're going to derive one essential rule, as well as talk about a couple other rules that we can use that are derived basically from rules for derivatives. So first we're just going to define the indefinite integral. If we have two functions, capital F of x and little f of x, we can define if f prime of x is equal to little f of x, we can define the integral of little f of x dx is equal to big F of x plus c. And this term can, this integral can also be written in a different form, if we can remember from a couple videos ago. If we take the limit of a sum over all I terms, f of x, I delta x, we also receive the same term. So it's exactly the same thing, except it's in a much more compact form. So now the reason why we're taking the integral, while we're taking the integral, we have a constant. We can do that from a simple example. So if we take the integral of 1, we end up with x plus c, because if you can remember from previous videos that the dx of x is equal to 1. So if we were to reverse engineer that, we can end up with the integral, the antiderivative of 1 is equal to x, but also dx of x plus 1 is equal to 1, because the derivative of 1 is equal to 0. So if we were to put this into our integration, our c could basically be 1, and if we replace 1 with 2, the same thing would happen. So basically it's saying that as long as the c is constant, any of these terms can be the solution to the integral. Okay, so now we're going to derive something called a power rule. So we know that there is a similar rule to this in differential calculus, which is the dx of x to the n is equal to n times x to the n minus 1. And we saw a derivation of this earlier on during our differential series. So we're able to derive a similar rule using this. So let's define something. Let's define n tilde to mu n is equal to n minus 1, and n is equal to n tilde plus 1 as a result. So let's just replace everything that's in here. So we have d dx of x to the n tilde plus 1 is equal to n tilde plus 1 times x to the n tilde. Because n minus 1, so if we replace n with n tilde plus 1 minus 1 is n tilde. So right now this is more of a hand-waving argument, but we can make the jump to turn this d dx into a fraction and bring the dx over here. This is actually a technique that is used quite a bit in differential equations, so it's something called separable first order differential equations, which we really don't need to worry about too much, but we can just accept that as true. Okay, so now we want to integrate both sides. If we can remember from a previous video, we kind of did a trick like this. So let's let a is equal to x to the n tilde plus 1. So let's just integrate dA equal to a plus c. So, and remember, a is equal to x to the n tilde plus 1 plus c. So we can say that this is true. So we have x to the n tilde plus 1 plus c is equal to the integral of n tilde plus 1 x to the n tilde dx. So now just to make life a little bit easier, let's just redefine, so we don't have to write the tildes over and over again. Let's just redefine n tilde is equal to n. So we're just basically getting rid of these n tildes. So let's quickly pause for a couple minutes to define a couple of the rules that will help us in further simplifying our integral. And both of these can be derived easily from differential calculus using the same technique that we just used. So, the first rule is the constant multiple rule. And using this constant multiple rule, as long as we have a constant k times f of x dx, that is essentially the same as saying k times the integral of f of x d of x. And once again, that this is essentially the same thing as the constant rule for multiplication for derivatives. And that can easily be proved using the same technique we just used on this example. And this is assuming that k is constant. second rule is the sum difference rule. Which doesn't necessarily help us in this case, but it will help quite a bit when we're working with polynomials. Where basically the integral of f of x plus or minus g of x dx is equal to the integral of each of these terms separately. So an integral of f of x dx plus or minus the integral of g of x dx. Once again, this rule can be derived using the derivative analog. So we want to use this rule because we know that n is constant. And we know that n plus 1 is also constant. So we're going to use the constant multiple rule to bring n plus 1 outside of the integral. So we have x to the n plus 1 plus c is equal to n plus 1 times the integral of x to the n dx. Now let's just bring the n plus 1 over. So we have the integral of x to the n is dx is equal to x to the n plus 1 over n plus 1 plus c over n plus 1. Now just the final step. Because n plus 1 is constant, c is constant, we can absorb the n plus 1 into the c. So let's just say c tilde is equal to c over n plus 1. We're just going to redefine c tilde. Now also, because c tilde is a constant, we can basically redefine, like we did earlier, c tilde is equal to c just for simplifying purposes. So we're able to make these changes as long as we define this to be true. So this is just saying that this constant is arbitrary. That they mean the same thing. So this is the rule of integration for powers. So one quick side note before we move on with a couple examples. N cannot equal -1. Because if we were to do this, n plus 1 when n is equal to -1, -1 plus 1 is 0. And you have that -1, you have the 0 in the denominator. So you'll be running into issues with that. In a later video, we'll be deriving an expression that will eliminate the need for using this for the n equals -1 term. Otherwise, we're good to use this. So I'm going to erase this and I'm going to rewrite the integration rule on the top of the board. And we're going to do a couple quick examples before the end of the video. Okay, so very quickly, the integral of x cubed dx. So let's just write this out. X to the n plus 1, where n is equal to 3. 3 plus 1 is 4, so we have x to the 4 over n plus 1. 3 plus 1 is 4 plus c. So let's quickly check this. The derivative of x to the 4 over 4 plus c. The derivative of x to the 4 is 4x cubed. So we have 4x cubed over 4 plus the derivative of c. The derivative of constant is 0. So we have 0. 4 divided by 4 is 1. So we have x cubed, which works. Next example is 1 over x squared dx. We can rewrite this to make this a little easier. So we have the integral of x to the minus 2 dx. They're the exact same things. So we can rewrite this onto the board. So x n is equal to negative 2. Negative 2 plus 1 is negative 1 minus 1 plus c is equal to negative 1 over x plus c. And just to check again, ddx of negative x to the minus 1 plus c. The derivative of negative x to the negative 1. So let's just do the derivative of x to the minus 1. The derivative of x to the minus 1 is x to the minus 2. It's negative x to the minus 2. So we have negative 1 over x squared plus the derivative of a constant, once again, is 0. So we have 1 over x squared, which matches. And just to give us practice with the sum/difference rule, we're going to do one final integral. So we have the integral of 3x squared minus 2x dx. So if you remember from the sum/difference rule, we can separate this polynomial into two parts. So we have an integral of 3x squared dx minus the integral of 2x dx. Now we can separate these integrals even further because we have constants in front. So we're going to use the constant product rule. So we're going to bring the 3 out front. Minus, we're going to bring the 2 up front. 2 integral of x dx. So 3, the integral of x squared is x cubed over 3 plus c minus 2 times x squared over 2 plus c. And we end up getting, and once again we can absorb the constants into each other. So if you get confused as to why we have two constants, don't. All I'm doing is basically just absorbing the constants into each other, because we can do that. We end up getting x cubed minus x squared plus c as our answer. So thank you for watching our video on the product rule and antiderivatives of polynomials. I look forward to seeing you back in the next video. Thank you.